So, if we recall our earlier discussions, we said that we have a lot of options regarding choosing our embedded core. It can be a microprocessor, a general purpose processor, such as a conventional microprocessor, which has got an instruction set that is regular enough to accommodate a wide class of operations, and it can be programmed, and it provides maximum flexibility to the programmer in terms of the number of applications it covers. The user only needs to bother about writing a block of code, a set of instructions for the processor, which we call a program, and once you run those programs on that general purpose processor, your system is ready for the particular application. On the positive side, it offers maximum flexibility to the programmer. On the negative side, your performance becomes severely degraded, because you keep on since it's general enough, it spans over a wide range of applications. Therefore, every time you need to write a program for a specific application, you have to cover that general enough instruction set, and then you keep on changing your instructions. And since the instructions are general enough, you cannot really have an option of optimizing the set of instructions for the specific application. These individual blocks separately. Each configurable logic block comprises of a 4-input lookup table, which is basically an 16x1 SRAM, a D flip-flop, and a 2-to-1 multiplexer. Each configurable logic block consists of a 4-input lookup table, which is a 16x1 SRAM. Yeah, I am coming to that. A D flip-flop and a 2-to-1 multiplexer. Now the question is, why this 4-input lookup table or 16x1 SRAM? The philosophy behind this 4-input lookup table is that I am storing the truth table of a 4-variable Boolean function, or less than 4-variable Boolean function in each LUT. Now, coming to this, a further enhancement over the basic CLV architecture, you can have an option of computing the carry directly without going through a lookup table. So, if you see the architecture of a FPGA, which is produced by some vendor, then the FPGA architecture, the CLB architecture of those FPGAs are somewhat different from the basic CLB architecture that we just studied. So one of the possible advancements can be that you use some kind of a logic circuit to compute the carry, because carry is something which we need to compute very frequently. So the CLB can have a carry logic sitting on it. Now if you see the structure of the 4-input lookup table, so it is basically comprising of a 16x1 SRAM, and then you are having a kind of marks tree with NMOS and implemented with NMOS and PMOS pass transistors. So for example, depending upon your input combination, one and only one path through this marks tree is enabled from the SRAM cell to the output. Suppose you give 0 combination, then this PMOS transistor is enabled, this PMOS transistor is enabled, this PMOS transistor is enabled, this PMOS transistor is enabled. That's why the content of this location is now available to the output. Suppose you give programmable switches. Now at the intersection of each horizontal and vertical wire, you have a programmable switch matrix like this, which is used for enabling or disabling the connections between horizontal and vertical lines. So at the intersection of each horizontal and vertical wire, you have a programmable switch matrix like this, with the help of which you establish a connection between horizontal and vertical lines. If we need to have programmable wires, which means anything you can program, any physical thing which you need to program, you need to make use of some kind of switch, right? Either you need a signal to program something, or you need to have a physical establishing or de-establishing of connection to do something. So if you compare the architecture of the two routing styles, in most of the FPGAs we typically have this segmented routing architecture, where you have local wires and global wires and intermediate things running over the same channel, and then you have to solve an optimization problem as to how many channels you have to keep and what will be the number of wires per channel. Similarly, in case of this hierarchical routing, the problem is to how to divide the FPGA into what many number of clusters, and how you will do the wiring within a cluster and between clusters. So now if you see the internal block of a typical FPGA CLB, you can see that it is somewhat more complicated than the basic architecture which we have studied. So you have, but now instead of just one 4-input lookup table, you have two 4-input lookup tables, and they are basically connected to another 3-input lookup table. So you have an option of implementing a logic function with 4 variables, another 4 variables over here, and 3 variables over here. So you can implement a logic function with 8 plus 1, 9 variables. You can implement a logic function with 9 variables. So these 4 variables plus these 4 variables plus 1 additional variable over here, which means you can implement a logic function with 9 variables using this CLB. Like the simplified architecture I have shown you, there are options for buffered as well as unbuffered outputs. So whether you will use a buffered or unbuffered output, it depends upon how you pass the signal through the blocks. And there are 4-to-1 multiplexers being provided to choose your path. Okay. So now let's consider a Boolean function. So it's basically two functions. You have x equals to a complement, b complement, and c or d, and y equal to a k or b k or c complement, d complement k, or a e j l. Now these two functions consist of 4 plus 4, 8 variables. So it can be implemented using one CLB of XC4000E. Now how to do it? You see that the function is embodied because you take k common, it is basically A or B or complement decomplement in the first three terms. So it is basically A complement, B complement and C or D whole complement. So if you take K, you are basically left with Kx complement plus AEJL, right? So that's how we can reduce this function. So AEJL is basically a 4-input Boolean function. It requires one CLB to be implemented, one LUT to be implemented, and X is another 4-variable Boolean function which requires one LUT to be implemented, and then finally you take the output of the two LUTs and provide it to the third LUT. So the input A is given to both the LUTs, right? So the K is given through this C1 input. It is available in the third LUT, and then AEJL is computed using this LUT, and then X is computed using this LUT, and then you are getting Y through this output port and X through this output port. So in both cases we required an unbuffered output, so we didn't go through the D flip-flops. We have directly taken the output without going through the D flip-flop. Now coming to the IO block, you can see that the same pin can be used both as an input as well as an output port. So with respect to the FPGA chip, mind you, with respect to the FPGA chip, the same pin can be used for both input as well as output purposes, but in most cases we get the chip as a part of the board, and because of the connectivity of the board, that means either the pin is connected to some input device or connected to some output device. So the board basically restricts the specific FPGA pin to be used as an input pin or an output pin. So from technology point of view, in an FPGA chip, the same pin can be used as an input or an output port, but because of the connectivity restrictions in the board, in which a pin is either connected to an input port or an output port, the specific pin in an FPGA chip is either used as an input pin or an output pin, not both at the same time. So now this is the external pin that is connected to this pad. Now this pin